Coaxial cable. Coaxial cable carries signals of higher frequency ranges than those in twisted pair cable, in part because the two media are constructed quite differently. Instead of having two wires, coax has a central core conductor of solid or stranded wire enclosed in an insulated sheath, which is in turn encased in an outer conductor of metal foil, braid, or a combination of the two. The outer metallic wrapping serves both as shield against noise and as the second conductor, which completes the circuit. This outer conductor is also enclosed in an insulated sheath, and the whole cable is protected by a plastic cover. Coaxial cable. It has inner conductor, insulator, outer conductor, and plastic cover. Coaxial cable standards. Coaxial cables are categorized by their radio Gorman rating. Each RG number denotes a unique set of physical specifications, including the wire gauge of the inner conductor, the thickness and the type of the inner insulator, the construction of the shield, and the size and type of the outer casing. Each cable defined by an RG rating is adapted for a specialized function. Categories of coaxial cables. RG59 impedance 75 ohm, use cable TV. RG58 50 ohm, thin in Ethernet. RG11 50 ohm, thick Ethernet. Coaxial cable connectors. To connect coaxial cable to devices, we need coaxial connectors. The most common type of connector used today is the by-one Neil Councilman BNC connector. Shows three popular types of these connectors: the BNC connectors, the BNC T connector, and the BNC terminator. The BNC connector is used to connect the end of the cable to a device such as a TV set. The BNC T connector is used in Ethernet networks to branch out to a connection to a computer or other device. The BNC terminator is used at the end of the cable to prevent the reflection of the signal. BNC connectors. Performance. As we did with twisted pair cables, we can measure the performance of a coaxial cable. We notice in figure 7.9 that the attenuation is much higher in coaxial cables than in twisted pair cables. In other words, although coaxial cables has a much higher bandwidth, the signal weakens rapidly and requires the frequent use of repeaters. Coaxial cable performance. Applications. Coaxial cable was widely used in analog telephone networks where a single coaxial network could carry 10,000 voice signals. Later, it was used in digital telephone networks where a single coaxial cable could carry digital data up to 600 Mbps. However, coaxial cable in telephone networks has largely been replaced today with fiber optic cable. Cable TV networks also use coaxial cables in the traditional cable TV network. The entire network used coaxial cable. Later, however, cable TV providers replaced most of the media with fiber optic cable. Hybrid networks use coaxial cable only at the network boundaries near the consumer premises. Cable TV uses RG59 coaxial cable. Another common application of coaxial cable is in traditional Ethernet LANs. Because of its high bandwidth and consequently high data rate, coaxial cable was chosen for a digital transmission in early Ethernet lanes. The 10/2 or thin Ethernet uses RG58 coaxial cable with BNC networks connectors to transmit data at 10 Mbps with a range of 185 meter. The 10 base 5 or thick Ethernet uses RG11 thickness coaxial cable to transmit the 10 Mbps with a range of 5000 meter. Thick Ethernet has specialized connectors. Fiber optic cable. A fiber optic cable is made up of glass or plastic and transmits signals in the form of light. To understand optical fiber, we first need to explore several aspects of the nature of light. Light travels in a straight line as long as it is moving through a single uniform substance. If a ray of light traveling through one substance suddenly enters another substance of a different density, the ray changes direction. Figure 7.10 shows how a ray of light changes direction when going from a more dense to a less dense substance. Bending of light ray: less dense, more dense. As the figure shows, if the angle of incidence I, the angle the ray makes with the line perpendicular to the interface between the two substances, is less than the critical angle, the ray refracts and moves closer to the surface. If the angle of incidence is equal to the critical angle, the light bends along the interface. If the angle is greater than the critical angle, the ray reflect and travel again in the denser substance. Note that the critical angle is a property of the substance and its value differs from one substance to another. Optical fibers uses reflections to guide light through a channel. A glass or plastic core is surrounded by a cladding of less dense glass or plastic. The difference in density of the two materials must be such that a beam of light moving through the core is refracted from off the cladding instead of being refracted into it. Propagation modes. Current technology supports two modes, multimode and single mode, for propagating light along optical channels, each requiring fiber with different physical characteristics. Multimode can be implemented in two forms: step index or graded index. Optical fiber. Propagation modes. Mode: multimode, single mode. In multimode, step index, graded index. Multimode. The multimode is so named because multi-beams from a light source move through the core in different paths. How these beams move within the cable depends on the structure of the core. In multimode step index fiber, the density of the core remains constant from the center of the edges. A beam of light moves through this constant density in a straight line until it reaches the interface of the core and the cladding. At the interface, there is an abrupt change due to a lower density. This alters the angle of the beam's motion. The step term index refers to the suddenness of this change, which contributes to the distortion of the signal as it passes through the fiber. A second type of fiber, called multimode or graded index fiber, decreases this distortion of the signal through the cable. The word index here refers to the index of refraction. As we saw above, the index of refraction is related to density. A graded index fiber therefore is one with varying densities. Density is higher at the center of the core and decreases gradually to its lowest at the edge. Figure 7.13 shows the impact of this variable density on the propagation of the light beams. Single mode. Single mode uses step index fiber and highly focused source of light that limits beam to a small range of angles, all close to the horizontal. The single mode fiber itself is manufactured with a much smaller diameter than that of multi-mode fiber and with substantially lower density. The decrease in density results in a critical angle that is close enough to 90 degrees to make the propagation of beams almost horizontal. In this case, propagation of different beams is almost identical and delays are negligible. All the beams arrive at the destination together and can be recombined with little distortion to the signal. Modes. Fiber sizes. Optical fibers are defined by the ratio of the diameter of their core to the diameter of their cladding, both expressed in micrometers. The common size are shown. Note that the last size listed is for single mode only. Fiber types. Cable composition. Figure 7.14 shows the composition of a typical fiber optic cable. The outer jacket is made of either PVC or Teflon. Inside the jacket are Kevlar strands to strengthen the cable. Kevlar is a strong material used in the fabrication of bulletproof vests. Below the Kevlar is another plastic coating on cushion the fiber. The fiber is at the center of the cable and it consists of cladding and core. Fiber optic cable connectors. There are three types of connectors for fiber optic cables. Fiber construction, fiber optic cable connectors, SC connector, ST connector, MT-RJ connector. The subscriber channel connector is used for the cable TV. It uses push-pull locking system. The straight tip connector is used for connecting cable to networking devices. It uses a bayonet locking system and is more reliable than SC. MT-RJ is a connector that is the same size as RJ45. Performance. The plot of attenuation versus wavelength in figure 7.16 shows a very interesting phenomenon in fiber optic cable. Attenuation is flatter than in the case of twisted cable and coaxial cable. The performance is such that we need fewer, actually 10 times lesser repeaters when we use fiber optic cable. Applications. Fiber optic cable is often found in backbone networks because its wide bandwidth is cost effective. Today, with wavelength division multiplexing, we can transfer data at the rate of 1600 Gbps. Optical fiber performance. The SONET network that we discussed in chapter 17 provides such a backbone. Some cable TV companies uses a combination of optical fiber and coaxial cable, thus creating a hybrid network. Optical fiber provides the backbone structure while coaxial cable provides the connection to the user premises. This is the cost-effective configuration since the narrow bandwidth requirement at the user end does not justify the use of optical fiber. Local area networks such as 100 base FX network, fast Ethernet and 100 base 1000 base X also use fiber optic cable. Advantages and disadvantages of optical fiber. Advantages. Fiber optical cable has several advantages over metallic cable, twisted pair or coaxial. First, higher bandwidth. Fiber optic cable can support dramatically higher bandwidths than either twisted pair or coaxial cable. Currently, data rates and bandwidth utilization over fiber optic cable are limited not by the medium but by the signal generation and reception technology available. Second, less signal attenuation. Fiber optic transmission distance is significantly greater than that of the other guided media. A signal can run for 50 km without requiring regeneration. We need repeaters every 5 km for coaxial or twisted pair cable. Third, immunity to electromagnetic interference. Electromagnetic noise can't affect fiber optic cables. Fourth, resistance to corrosive materials. Glass is more resistant to corrosive materials than coppers. Fifth, lightweight. Fiber optic cables are much lighter than copper cables. Sixth, greater immunity to tapping. Fiber optic cables are more immune to tapping than other copper cables. Copper cables create antenna effects that can easily be tapped. Disadvantages. There are some disadvantages in the use of optical fiber. Installation and maintenance. Fiber optic cable is a relatively new technology. Its installation and maintenance require expertise that is not yet available everywhere. Second, unidirectional light propagation. Propagation of light is unidirectional. If we need bidirectional communication, two fibers are needed. Cost. The cable and the interfaces are relatively more expensive than those of the other guided media. If the demand for bandwidth is not high, often the use of optical fiber can't be justified. Thanks for watching this video. If you found this video helpful and want more videos like this, then please let me know by click on like button and subscribe to my channel. Thank you.